Okay, good morning to all. I am Dr. P. Gopinath, Assistant Professor, Selection Grade, Department of ECE, KIT, Kalaignar Karunanidhi Institute of Technology, Coimbatore. Today we are going to discuss the subject is Digital Signal Processing, B23 ECT 404. So in this DSP first unit is a fast discrete Fourier transform. So in this discrete Fourier transform, we have used a more number of additions and multiplications, and also the computation speed is very high. That is a complexity, that computation complexity is very high, so that we have moved for next transform, fast Fourier transform. So in this fast Fourier transform, we have performed using the same DFT formula, using the two properties, major two properties, that is a periodicity property and a symmetry property. Then in this discrete Fourier transform, number of complex multiplications, generally we have calculate n square. Then number of complex additions, we have performed n into n minus 1. So these are the important factors, important calculations. It is somewhat difficult to perform processor, so that we have go for fast Fourier transform. This is the classification of fast Fourier transform. That is a computation of DFT should be divided two parts. First one is a divide and conquer approach. Then second one is a DFT as a linear filtering. This linear filtering consists of two algorithms, that is a chirp Z transform algorithm and Ghostal algorithm. In first primary part, divide and conquer approach, using we have three algorithms, that is a radix 2 FFT algorithm, radix 4 FFT algorithm and split radix FFT algorithm. So these three algorithms based on time domain and frequency domain. So based on time domain and frequency domain, we have classified DIT FFT algorithms and DIF FFT algorithms. That means decimation in time and decimation in frequency. So first we are going to see that radix to decimation in time FFT algorithm. So in this FFT algorithm, we are using DFT formula. So we know very well about DFT formula, x of k equal to n equal to 0 to n minus 1, x of n, wn, kn. We have split above summation into even and odd values. In this decimation in time, we have split that two parts, that is even samples and odd samples. So that number of samples should be divided. That is a x of k equal to m equal to 0 to limit value also change. That is a n by 2 minus 1 x of 2m, then wn 2km plus summation m equal to 0 to n by 2 minus 1 x of 2m plus 1 wnk into 2m plus 1. Then f1 of m we have considered even samples, that is x of 2m, and f2 of m equal to x of 2m plus 1. So here we have substitute m value is 0. In this condition, m equal to 0 means we obtain all the even values. Then likewise f2 of m, that is equal to x of 2m plus 1. So here we have substitute m equal to 0. We have obtained output values are all the values are odd terms. Then the formula should be denoted x of k equal to m equal to 0 to n by 2 minus 1 f1 of m w n power 2 km plus summation m equal to 0 to n by 2 minus 1 f2 of m w n 2 into km w n power k. So here we know that w n power 2, that is a using Tudel factor condition, that is a we have write w n by 2. So both are equal. So in this condition, we have represented That is a Wn by 2 we have write. Instead of Wn power 2, we have write Wn by 2 Km. Plus, here the common term, the total value Wn power K take outside, then remaining values are there. So in this equation, we have considered capital F1 of K using DFT formula, discrete Fourier transform formula. That is small F1 of M is nothing but is converted into frequency domain. That is a capital F1 of K plus total factor value Wn power K. Then F2 of M is converted. That is a frequency domain representation. We have denote F2 of K, F2 of K, replacing by K plus N by 2. That is X of K plus N by 2, that is equal to F1 of K plus N by 2 plus Wn K plus N by 2 of F2 of K plus N by 2. So here we are using periodic condition, periodicity property F1 of K plus N by 2, that is we have write F1 of K. And F2 of K plus N by 2, we have write F2 of K. So here Wn power K plus N by 2 is nothing but minus Wn power K. That is the second equation. In this equation, you have denoted X of K plus N by 2, that is equal to F1 of K minus Wn power K into F2 of K. So these two equations called decimation in time equation, DIT equation. So these two equation illustrated here, that is the first one, equation 1 is X of K equal to F1 of K plus Wnk F2 of K. And for the limit value K equal to 0 to N by 2 minus 1. Similarly, using periodicity property X of K plus N by 2, that is nothing but F1 of K minus Wn power K F2 of K for K equal to 0 to N by 2 minus 1. So here flow diagram should be illustrated. Here first 4 point samples we have considered even samples. Then second 4 point samples consider odd samples. So based on bit reversal condition, we have obtained X of Z. Here, yeah, 8 point we are going to perform. So 8 point samples like 0 to 7 values are there. It should be converted into bit reversal order. That is a X of 0, 4. That is a first even samples X of 0, 2, 4, 6. Then odd samples 1, 3, 5, 7. So in this 4 point DFT, we are using above formula. We obtain capital X of 0 to X of 7. So this is the flow diagram. So this is 8 point flow diagram. This 8 point flow diagram, that is a first step is converted. That is a input input sequence is converted into bit reversal order. The bit reversal order for n is 8 point is 0426 1537. 04261537. So in this condition, so this is the 2 point structure. This 2 point structure is converted into 4 point. 4 point should be converted into 8 point. So in this tabular column should be denoted. That is a difference between direct computation versus FFT algorithm using. So this is DIT. That is a radix to DIT FFT algorithm and flow diagram. Thank you.